Hello everyone, welcome to this class. I have the class that is at the end of the day, so let's try not to sleep and let's keep the lecture interactive. So welcome to the Design RISC-V Energy Efficient Edge Node Systems on Chips. We will see today what actually the title means. And I'll first introduce you to how the class will be structured. It's in 4 days, so Wednesday there's no class. The first day, so today, I'll give you an introduction about what RISC-V is, what the energy efficiency, system on chips. We learn a bit the vocabulary and we align on the backgrounds and so on. Then tomorrow we'll jump to the RISC-V CPUs. Then we see how to extend the RISC-V CPUs to have to be more efficient, more performance, and so on. And the last day, so Friday, we will play with the microcontroller. So we will go, let's say, at a higher level and see where these CPUs are instantiated into, accelerators, and so on. Also, at 6 p.m., so after this lecture, which ends at 5:30. In another room, which I guess is going to be in the other hotel, we will have another talk, which is based on the RISC-V ISA. So whoever is interested from here, we go all together in the other room, in the other hotel, and we keep on talking about RISC-V at another, not a technical level, but in another level that I guess could be interesting for many of you. So, first of all, let's introduce each other. Hello, I'm Pasquale Davide Schiavone. Simply call me Davide, please. I'm Italian, but not from Rome. I'm from Turin, where I studied and graduated, both bachelor and master. Then I went to Zurich in Switzerland, where I've done the PhD. So I guess in your slides you have written that my affiliation is ETH Zurich, and actually it's also here, but it's wrong. I was ETH Zurich. Then I graduated. And now I currently have 2 positions. One is postdoc at EPFL, so I moved from Zurich to Lausanne, still in Switzerland. And there I'm keep on doing research and extending what I've done in Zurich. But also I have another position, part-time, with the Open Hardware Foundation that I'll introduce you later, but it's a non-for-profit foundation as RISC-V that curates open source IPs based on the RISC-V ISA. So, this is the lab where I work on. It's called Embedded System Laboratories. So what they do is embedded system, mainly. The professor is called Davide Schiavone from Spain. The group is quite big. There are many PhD students. One is actually here. Postdocs, research associates, and so on. And we work on many different projects, both industrial and we collaborate with companies and so on. And also we work on education only, or let's say pure research only projects. What I like about this lab is that it's quite holistic, meaning that of course we care about electronics and embedded systems, so the domain is defined, but the abstraction hierarchy is very flexible, so there are a lot of people that work at application level, so they are trying to optimize the application, they are making it faster, smaller, more efficient, more accurate. I guess many of you have been playing with AI and machine learning algorithms, so there are a lot of people playing with Python, PyTorch, all these tools that I'm not very familiar with to make the application nicer, let's say. Then there are a lot of people that are deploying these applications in embedded systems, so they're actually building wearables, for coffee machines or smart glasses, smart watches, and so on, and they are trying to optimize how this application is actually deployed in the embedded systems, together with the design itself of the system. And then down to the hierarchy, we go to the hardware side, where I'm actually coping with, which is designing the system, so the system on chip. We will see later what it means. Playing with the architecture to accelerate it, to make it more, let's say, smaller or bigger or more performant, less power, less energy, whatever the goal is, down to circuits. So we actually do chips. We actually send what we are doing to manufacturing, then we get the chip back and we build this new systems based on the chip we actually designed. not only the hierarchy stack is actually very, I would say, wide, but also the nature of the application. So there are people working on, for example, smart cities, industrial applications, and so on. But also many people working on, let's say, health applications, so monitoring the heart, the ECG, EEG, and cough detections is also another application we are working on for monitoring COVID or things like that. And so as you see, it's quite a wide domain. It's a very nice lab because you can meet people with a lot of different backgrounds and working on different things. That is actually very inspiring. Okay, so first of all, that's the title. I try to break it in several pieces to go down to the context. So now everyone is familiar with the word context. So we start from the system on chips, but before that, I actually have questions to you. Who is working already on system on chips? Okay. I would say 30%, maybe more. So what are you doing, guys? Are you working more into RTL design, implementation in silicon, implementation on FPGA, or what?
RTL design.
RTL design. And down there?
Yes, same.
Also RTL design? Okay. So you're doing actually chips? Okay, nice. How many of you are doing chips? Okay, of course. 1, 2, 3, 4. Okay, very few. Very few because it's expensive and it's actually a lot of engineering work. But it's actually very nice, I love it, honestly. And actually I'm spending my day doing one now in the hotel. But okay, so all the others are coming from computer engineering or electronics, or just to understand the background and tailor a bit the introduction towards the majority of you. Are you working on computer engineering, writing software for embedded system? Few? AI? Bro, no, very little, okay. Anyway, just a bit of context. Back in the days, let's say the 60s, the 70s, 80s, stuff like that, usually every IP in a system was a discrete or it was its own chip. So you had the CPU chip, the memory chip, the peripheral chip, and then you were assembling them on the motherboard, PCB, whatever you were assembling them on, while technology scaling allowed to put more things on a single die. If I say words that you don't know, just please ask. Don't be shy. So that means that the CPU, part of the memories, some other peripherals and so on, ends up in the same system, which is printed and manufactured all together. So when you get back the chip, it's actually not just a CPU or just a memory or just a peripheral, but it's a lot of things together. And they can work quite autonomously because they have a lot of capabilities. Those are two examples of chips. And what is important is that today, because technology scaling is very aggressive and so on, there's a lot of area available, or let's say a lot of the transistors are very dense. So you can actually put there also accelerators. To accelerate what? It depends, of course, on the chip you want to design. Most of you are probably familiar with the NVIDIA GPU, so they are trying to accelerate, for example, workload that is very digital signal processing oriented. So, for example, machine learning is one of them. Then there are graphic cards. They can also be used for graphic cards, but there are also security chips. So system on chips that are actually tailored around crypto functions or stuff like that. But what is common among all of them is that in the single die there are a lot of stuff. Okay, so this is what system on chips are. Then I mentioned a few, like the NVIDIA GPUs or security functions and so on. But actually, what defines, I would say, a system on chip is actually the domain it's gonna work on, right? So designing a processor that is going to run on my laptop, or designing a processor that is on your smartwatches, or designing a processor that is in your smartphone is completely different. They're called processors, but they are completely different. They execute different kind of workloads, so the software is different. They execute, they run on different processors. The nanometer of the technology node is actually usually different. The energy consumed is different, or the power. So some of them consume watts, so you heard the watts into, let's say, for the GPUs, or even more, while the ones on your smartwatches are milliwatts, so they're completely different profile of power consumption, but also the size is different. So I don't have a picture here, but the processor on a server are maybe like this. So you maybe have the package with all the cooling around and so on, because they dissipate a lot of power and so on, while the ones on your embedded system, on your wearables, are very tiny, very, very tiny. Even with the package, they can be weared on rings or smartwatches, earphones, and so on. So as you see, they are very different. So because I wrote here edge node, let's define what CPUs I'm talking about, what system on chips I'm going to talk about. So those, as you see from the images, they are for wearables mostly, and they are at the edge. Why at the edge? Because they are very close to the sensors. They are very close to the application they're going to run. They are very close to the data they are gathering. So for example, if you're designing a system for processing audio, coming from a microphone, this guy is very close to the microphone. So that's why at the edge. So if you write an application, for example, in Python on your laptop that gets data from Bluetooth from your phone, and in your phone you're recording your audio, that's not really edge. Maybe yes, it's not really defined what edge means, but in this case you're recording from your phone, you're storing this file, you're sending it over the network, let's say Bluetooth, Wi-Fi, whatever network is. You're getting it on your laptop, and then you're running the application. Or even worse, if the application is really big and requires servers capability, you have to send it to your laptop, and then the laptop sends it over the network on the cloud and so on. That is not edge. It's not really close to the audio. What is edge is actually on the device you are recording, you are also processing or pre-processing. Of course, if these guys are battery powered, or if they are small because they are embedded, that's why the name embedded, embedded close to the sensors, they need to be small. Usually they are battery powered, so they need to consume little power. So of course the capabilities that these guys have are completely different from the CPUs that you buy for your server, right? So in your server you will have clusters or multi-core with dozens of pipeline stages running at gigahertz, consuming watts, while here you have small CPUs running at megahertz, at the best case, consuming few milliwatts. So of course the computational capabilities, so the number of operations per second, are much lower. I'm trying to put here and there a few words, we are gonna define them also later. And but still, these guys needs to run several applications, right? Of course, I can design a single CPU that does only one function. For example, if you are familiar with audio applications, usually you transform the time series into the frequency domain, so you can design an FFT chip that does only Fourier transform. Fine, cool. But what if you change the application later on? Maybe you change the way you implement it, or the frequencies you care of, or you want to do another kind of pre-processing before the FFT, whatever. You need to update the firmware, right, or the software or the function. So you don't really want to do a very application-specific CPUs. You want to be them a little bit versatile, such that you can update. Still tailored on your application, but we will see these things later. Questions so far? No. Okay. Then the third word is RISC-V. We are going to talk about RISC-V mainly the whole lecture today. So for now I'll just give you an introduction. But as I said before, you need your system to be versatile, right? One way of making a system versatile is to let it run software. For example, written in your favorite language, that could be C. or could be C++ or whatever. So you write your application, and then you deploy it on your microprocessors or your system on chips for your audio application or whatever. Then in the future you want to change it, so you modify the C application, but not the hardware. Changing the hardware is expensive. And so that's why we want them to be programmable. A programmable IP is a CPU. So a CPU is a complex finite state machine, right, that execute the instructions. And these instructions can be compiled. It's true that your program, it's written in C or C++, but then they get translated to some binary code, 011100, whatever, right? And the definition of this guy is actually the ISA. We will see it later, the instruction set architecture. And in this class, I'm going to say and present you why we should care about the RISC-V ones. For now, I'm just making segments of the title. And finally, I repeated it many times, these guys needs to consume little power because they're battery powered, whatever, so you don't want to charge them every minute. It's already boring that today we have to charge our mobile phone at least the use I do twice a day. And so you don't want to do that, right? Not too much. So they need to consume little power. They need to process the data. Before I mentioned the FFT, but we are in the AI area, so you want to run very complex algorithm, not only pre-processing, filtering, Fourier transformation, but real neural networks on your CPU to understand, for example, whether your audio signal contains a wake-up word, hey, wake up, or I don't want to make publicity to commercial devices, but hey, someone wake up your system, right? So there is something that is processing this audio time series and understands whether you want to wake up the device or it's just noise or it's just another command. Okay, if you want to implement that, you have to, for example, implement a neural network. That's a way to implement it. So you need to do a lot of instructions, a lot of computation within a small power budget, right? Or if we get a smart camera for security that wants to detect whether there's a person or not into the images, again, you have to run, for example, CNN, and again, a lot of mathematical operations within a small power budget. So that means being energy efficient, doing a lot in a small power budget. That means energy efficiency. Okay, so that builds the title for today. Do you have any questions? How do you implement energy efficiency if you work on energy efficiency on during your PhD? I guess most of you do the PhD or a master degree. How do you implement energy efficiency? It doesn't need to be hardware, it can even be software, for example, or application. You do a
profiling to see where you have to optimize, and then what I do is map to hardware, like the most power-hungry section of our code, I map it to hardware.
Okay, so just to repeat for the camera, he profiles the application, and the most power-hungry sections are accelerated in hardware. That's what you mean, right? Are you working on FPGAs, or how do you accelerate the hardware?
I develop functional unit for RISC-V code.
Okay, so you will be working on 2 days, or no, in 2 days lecture we will see ISA extension. So he accelerates by adding custom instructions to his own CPU. Or another example in applications, what do for example, the AI companies are trying to do? Are they using quad precision floating point units numbers for weights of your own transformer or neural network, or 8-bit integers? What would be the difference here?
They use quantization and pruning for that.
Yeah. So why is that an energy efficient optimization, for example?
It's less computation.
Okay. Yeah, actually the number of multiplication is the same, but the multiplication itself is cheaper.
Exactly.
because you don't need a lot of bits to represent your quad precision floating point number. So that means a lot of stuff, right? So if the data are on DRAM, you go to the DRAM less times, or maybe your hardware is faster in computing 8-bit multiplication instead of quad precision floating point and so on. Okay, so we saw the custom hardware, we saw custom, let's say, application. Are there other ways to do energy efficiency?
Power gating and clock gating.
Okay, so he says power gating and clock gating, so that means translating it is switching off what you are not using. That will reduce the power, so you keep the computation the same, but you consume less power, so the product is more energy efficient.
Reducing the RAM movement, so enhancing the
Yeah, so this is closer to, for example, the DRAM example. So you keep data closer to the processing element, so they travels less on the wires and of your system. So that means less switching activity on your capacitors, so less power.
Software managed caches and branch prediction.
Okay, so making caches smarter to have less penalties, and so again towards the data locality. Compiler optimization, so for example making the software faster or smaller.
using a 32-bit processor instead of a 64, for example.
Yeah, okay. Using smaller processors, yes. Instead of 64-bit 32, so consuming less power, for example, if your application is okay with that, and so on. So as you see, there are a lot of ways to reduce the energy. There's no a single way. But every one of you suggested something that goes into the direction that you need domain specialization, right? So if I'm a company and I get asked to make a chip energy efficient better than what the market provides for audio processing, 100%, probably in all the layers, applications, deployment, hardware, and even silicon implementation, I'm going to add something that is specific to what I'm doing. Which doesn't mean I have to give up all the versatility. Can be, of course, that will be even more energy efficient. I will need to do a trade-off, for example, because we said hardware is expensive and I don't want to make a chip every second week, especially as the applications are growing quite fast. But for sure I need a specific function somewhere to make my application better or more energy efficient, or running faster or consuming less power and so on. So all the examples you actually suggested to me before are somehow a domain specialization strategy. Some of them are very generic, like power gating and clock gating, that is applicable mostly in every domain. Some others could be more tailored. For example, if I build an accelerator, like before your colleague suggested to add custom instructions. If I add the custom instructions that is really good in doing the FFT, what I'm speeding up is FFT. So if I'm building a CPU that has to do crypto functions with hash and so on, the FFT is not useful. So in that case, it's specific to that domain. So for audio could be useful, and for security won't be useful, and vice versa, right? So if I have an AES accelerator, is useful for my crypto chip, but it's not useful for my neural network image compression chip, for example. And of course, you can add many of them all together. What I want you guys to take home is that there's no one solution fitting all. You have to, as your colleagues suggest, profile your application, understanding exactly what you need to be better than the state of the art. If you're doing the PhD, your state of the art is a paper. If you are a company, the state of the art is your competitor, the one that you want to beat. If you don't have competitions because you are doing something completely new, you want to be efficient in doing things with good numbers, right? You don't have a reference, so you can do whatever you like. Okay, so are these solutions energy efficient? in whatever they are doing?
Depends.
Depends is the universal answer.
Mass
But
for a train would be more energy efficient if you have to transport many people.
exactly. So just to repeat, if their goal is carrying a lot of people from Rome to Fuji, for example, like the bus you most likely took to come here, they're not energy efficient, right? Because you will need many of them to come here. Or are they energy? So he said no. Is there anyone saying yes?
Yes. For the job that they are designed to.
Okay, so what's the difference? Because, for example, if we divide them in two, here are 2 wheels, there are 4 wheels there. So what are the difference between them? You don't know them?
Designed to race or designed to, I don't know, cross a mountain. Like with the Jeep, you go through the mountain with the one you race in Monaco, I don't know.
Yeah, yes, exactly. Yeah, so they're designed for different contexts. So if I take these two, I prefer motorcycles, so I get this side. But if you take these 2 guys, they're both designed to be fast, right? Do you agree? It's quite recognizable that these 2 guys are doing a competition for arriving first. But the road is completely different. The MotoGP one on the bottom needs to be the fastest in that kind of track. And the one on the top needs to be the fastest in another kind of track, with other rules. So what is the context between these two? Different rules, different tracks, and different rules is not one rule. It's the kind of engine, the amount of fuel, the CC, the dimension of the engines, a lot of stuff, right? If you are more familiar with F1, Formula 1, there are thousands of rules you heard of, right? You need to be this size, you have to use these tires, you have to, those are the rules. So this defines your context, that's your application. So what Ferrari and Ducati, of course I'm Italian, so I picked Ferrari and Ducati. If Ferrari and Ducati got as a job, be the fastest on, someone said Monaco, I can say, for example, be the fastest in Le Mans. Okay, so if actually they do optimization in every track. In every track they fine-tune the engines and all the stuff that they can fine-tune to be the fastest on that track. So they optimize all the profiles and so on. So they got the application, being the fastest here. The state of the art in MotoGP is actually Ducati itself. In Formula 1 I have no idea, but it's not Ferrari. So they are trying to work to be the fastest there, right? Whereas whoever designed the electrical scooter there or the electrical 500 on the car side didn't, of course its goal was not being the fastest in Monaco, for sure, because they would have failed. For them, probably the goal was consuming as little as possible. So their clients are, let's say, environmental friendly, they don't want to pollute the air and so on. So they're completely different. And the ones that is going to the mountain is maybe still wants to be the fastest, like the other, the F1 or the MotoGP, but still it's another set of rules, different engine dimensions, different tracks, different rules. So the design, the best design is completely different. So these 2 guys have in common just 2 wheels, the fact that they have 2 wheels, that's it. And probably that they require gas to run, full stop. The rest is completely different, exactly like between the 500 and F1 and the Ferrari, they are completely different. Okay. So putting things all together, if you want to design your own energy efficient whatever, it can be the car or the system on chips, as we are here talking about system on chips, is most likely your system. You want them to be programmable, again, because there are a wide set of applications, or your application is not fixed, can require updates, as for example, you're updating the weights of your neural network, or you're updating the model itself. You moved from a CNN to a transformer, for example. So we want programmable system on chips. These guys are at the edge. They process data coming real time. So for example, my voice is usually sampled. I'm not an audio expert, but for example, audio is usually sampled at 44 kilohertz, I guess. I don't know, is anyone expert in audio processing? But I guess it's 44 kilohertz, the default frequency. And that is a timing constraint, right? It means every 1/44 milliseconds I need to be ready to get the next sample and to process my window of data. And this guy, because they are at the edge, are usually battery powered. So they need to consume as little power as possible, which means altogether, so real-time constraints plus battery power means energy efficiency. Then depends on the domain, and in the next days we will see different domains and how different solutions can be required to implement energy efficiency. Okay, so this is a summary of what I said before. We said programmable and versatile, perfect. Now, reuse of high quality IPs, we will see that later. I just put these slides here because when you will be back at these slides, you will see how things are gonna link all together. So you need high quality IPs to design your system on chips. We will see what it means. When you are trying to design it, you want to target multiple platforms, so ASIC, FPGA, for different reasons. And RISC-V is open source. We are gonna say why also open source is important. So we are ready to start RISC-V, I would say. Questions so far? This was the introduction. Did you get more or less where we are going? Yeah? I know it's 5 p.m., but you have to make questions, huh? Okay, so how many of you knows what an instruction set architecture or ISA is? Okay. Everyone mostly. And how many of you, like me, like to see the assembly generated by your program? Okay, so I'm not the only nerd here. Okay, cool. Okay, I guess the last step, no one is doing it except unless you are debugging the custom extensions. But yeah, so what an ISA is a contract, I would say, between the hardware and software. So you have a piece of hardware running some operations, where some is to be defined, and then you have your software that needs to be translated to those operations, right? So the spec between these two words is the ISA. So if, for example, you're doing a matrix addition, maybe you've write it in C code, like the example I'm showing here. And when you compile it, if you're compiling it for your own laptop, most likely you're using an Intel, for example, and you look at the generated assembly, you will see the Intel ISA. If you compile it for RISC-V, you will see in the example that you have in this slide, the RISC-V ISA. If you're compiling for ARM, you will see the ARM ISA, and so on. But the C code remains the same. Do you all agree? That's portable. That's the software should be portable. And the ISA is basically masking or translating a portable code to a specific hardware. Where specific also is, we will see what it means. And then this is the readable assembly, the one on the top. Then gets translated to what the machine can read, which are only 0 and 1. It's actually the same. They correspond 1 to 1. Okay, so this is an ISA. What is RISC-V? It's an ISA. So that means it's a specification that contains this number of operations. So they define the operations to be done, and they define how they get translated to 1 and 0s. So they're coding. Why do we care about RISC-V? Why are we talking about RISC-V and not another ISA? Because it's not the only one, right? I could have done the whole slides based on ARM. It would be the same, right? Theoretically talking. What is nice about RISC-V, and we will talk about it even more in the next talk at 6 p.m., is that you have the freedom of using it, which means you can see actually exactly the spec and how they get translated. It's open. It means you can design the hardware to implement a RISC-V CPU by yourself. You don't have to buy the license from RISC-V to do it. So it's free. Many of you maybe don't appreciate what it means, because who cares? But actually you care if you want to design an ISA. Either if you do, both if you do a PhD and if you are in a company, right? Because you don't want to pay to design a CPU. Someone that define the spec, where someone are, for example, the ones I listed before. So it's an ISA, it's open source, fine, you have the freedom of using it. It's, let's say, handled by a foundation, which is non-for-profit. So it's an org, which is based in Switzerland, by the way, I think in Zurich, if I'm not wrong. And of course, it's, again, the ISA itself is versatile. Why? As we said that before, you can use 32-bit instead of 64-bit. Someone else may need 128-bit. Someone needs to add custom extensions. Someone else is using the CPU to do FFT. Someone is using it just to control the temperature of your chip, right? So because of the different constraints we listed before, also RISC-V is trying to be flexible to, you know, to implement whatever you need, and to not, you know, it doesn't oblige you to implement what you don't need, which is both sides are important. And the rest I will say it later. But it's an active community, so there are conferences and so on. But let's stick to the technical side. So we say that it's open source, it's simple. Simplicity is very important because it translates to the complexity of hardware. It's an ISA, is well defined, simple. You can write efficient hardware, simple hardware. Usually simple hardware is also efficient. And it's modular and well structured, meaning that the privilege and privilege spec and all those things that defines what the CPU can do or is allowed to do or not is separated than the computational instructions, and the modularity allows you to not implement what you don't need and to add modulars that you need. So if you are designing a CPU that is good for security, don't add those extensions that don't help you with your security applications, and vice versa. Okay? So there are a lot of companies. It's not a toy example. It's actually many companies are investing in RISC-V. There are a lot of both commercial products and non-commercial products, open source and closed source implementation of CPUs based on RISC-V. Here you see a few of them. And what RISC-V does is making mandatory only a subset of instructions, so you can call your CPU a RISC-V CPU if at least it implements the integer extensions. So those are called I. So like the first example here. Then you can decide yourself whether you need a 32-bit machine or a 64-bit machine. How? Maybe as your colleague suggested, by profiling or doing whatever, or maybe you got an application that is already tested with 64, so you need 64. And then you have generic extensions that you may add or not add. For example, do I want my CPU being capable of doing multiplications and division in hardware? If the answer is yes, they define multiplication and division, let's say, extensions. Those are standard, they are RISC-V, but you are not obliged to add them if you don't need them. Again, with atomics, floating, double, and many more. So we will jump a little bit into the specs into the next slides. Then maybe some of you are already familiar with compressing instructions. Then where it's very expensive today in your system is memory. Memory is big and it's costly and consumes power. So if your CPU is executing these instructions, you want to, for example, encode an addition instead of 32-bit, 16. This is an example similar to the one we just did before. My application as a model with quad precision weights that I'm quantizing to 8-bit. This is not quantization, it's compression, so there is no data loss. And it's just a way to say the same thing with less bits. So that means it's faster and consuming less power executing compressed code. So what they did is profiling what is the most common instructions in generic code, and for those instructions they defined a compressed version. These overalls reduce the size of your program by 25-30% more or less. Okay, so this is very important for you, and especially in the context of energy efficiency.
Sorry, is it like ARM Thumb?
Similar concept, yes. Then what do you notice here? Anyone designing hardware? What do you see here? Exercise, write a decoder for RISC-V. What do you do?
Look at the first 7 bits first.
Yeah, exactly. So that is part of the simplicity. The encoding is simple because it's regular. So your decoder, if you write in Verilog, for example, your big case, switch case, is actually regular. First you look at this, then you decide whether the instruction is R, I, S, U, and then you have sub-switch cases to decide what to do. Do I need to read the 2 operands from the register file because it's an R type, or I need only to read 1? Do I need to encode my immediate value because I'm adding a constant number to my register? For example, add register 1 with number 7. Do I need to do that or not? Do I need to do an addition or subtraction, and so on and so forth? This is defined here. Now, what is different from many other architecture is that the register file is general purpose, meaning that you can use, it defines 32 registers, first of all. They are from X0 to X31. X0 is always 0, fine. We saw that in other ISAs as well, fantastic. But in other ISAs, there are some registers that are specifically the stack pointer, the global pointer, the stack, the whatever, the return address, and so on. Whereas here is actually the special registers are the same of the general register. So it's up to the software for conventions deciding whether which register to use. Of course, because we want to have easy life, we have some conventions when we compile. So between us, we define what the return address is usually mapped to, for example, X1. So when you compile the application, when you do return, there will be a jump to X1. But X1 is still general purpose, meaning that if you write assembly, you are completely allowed to use X1 to do whatever you like, an addition, a subtraction, and so on and so forth. So this reduces the number of mandatory registers you need to have, and it simplifies your architecture again. Then if you implement floating point instructions, because we saw before they are not mandatory, they are modular, then you need also another register file for floating point operations. But we will see that later. Okay, so what kind of instructions do you have on your CPUs? For those that already looked at the assembly of whatever they compiled. What do you usually have?
Branches.
Branches, yeah. I wouldn't have said that as first, but yeah, for sure it's mandatory. Load and store, why? Yeah, but we did, what I didn't say, but it's important to say, it's a RISC. It's the RISC architecture, right? So you cannot you cannot have instructions referring to memory. Those are CISC architectures. You need to have them in register, so you need to communicate with the memory in an explicit way. This is done with load and store, yes, so it's a RISC-V, it's a RISC, architecture. Then compute instructions, addition, subtraction, stuff like that, shift, or XOR, and when you write in your application if something is happening, how this is done, it's with Boolean operator. Okay, so pretty much those, right? Then you have other kind of so it's quite simple, isn't it? The base ISA, the baseline, is quite simple. Then of course you will see some more exotic ones like UIPC, which allows you to interrogate the program counter. This is used to, for example, jumps to some places. Then branches, someone said branches, that are conditional and unconditional. So jump here if something is happening, or just jump there. For example, return. We don't have to test a condition to return from a function. That is a jump. Okay? Quite simple. Questions? Who has ever looked at the ISA of Intel, for example? Yeah, what's the difference?
Intel, at least at the time that I was looking, it would have a variable length of instructions. So
Yeah.
1 byte, 2 byte, 3 bytes.
Yeah. So how do you write your decoder?
Sorry?
How do you write your decoder in, for example, Verilog or VHDL, whatever? Is it more complex or
It's more complex
easier than this?
usually than you
Exactly.
have variable.
Yeah. Yeah.
And then there are a lot of reserved instructions that
So other kind of ISAs are more complex because they have variable length instructions. Some of the things are reserved. You cannot freely use all the registers on the instructions, so you need to, be careful with what you're writing. If you're writing assembly, or whoever wrote the compiler needs to know all these rules and to keep them into account. Other people playing with other ISAs?
There are many different implementations of, for example, the add instruction, depending on what your so it's a memory access, or if it's so not just one fetch and one add.
Yeah, but so there are different kind of additions, but for example, or different flavors of the same instructions depending on the operands. This is the same here as well, because you can have operands can be both 2 registers or 1 register and an immediate. That's the case for RISC-V as well. But yeah, I agree with you. Is less cases. So it's again. So the message here is, remember that the designer of RISC-Vs wanted to keep the ISA simple. Okay, that's the message, or at least in its base form. Okay, so we will see a few examples of extensions of RISC-V that are RISC-V extensions. On Thursday, we will talk about custom extensions. Custom extensions are not RISC-V, but are compatible with RISC-V, but they are not defined by the RISC-V Foundation. So that means that whatever is defined there, it's you guys, users of RISC-V, defining it. It's not the foundation. So a program compiled with RVI, for example, so the integer and Boolean and arithmetic operations for RISC-V, can run in every RISC-V core. Do you agree? Because they all implement the same spec. Do you agree? So if you compile your application with the flag RV32i on your compiler, and both your processors and your processors are compatible with that, no, they are compatible. So they work. Custom extensions, it means it's me customizing the CPU, which means that my code compiled for my custom extensions doesn't run on your core, that doesn't implement those custom extensions. That's the main difference. Question?
If I have RV32 compiled code, can I run that on RV64?
No.
Okay.
No. No, because they will, so the question was that if 32 and 64 bit compiled programs are compatible with each other, the answer is not, but in 64 you can have 32-bit instructions. So for example, you can say load 32-bit, but you cannot say load 64 in 32. Okay? So if we agree each other, we can run the same code. That's true for every ISA, not just RISC-V. So a question for you guys. If I compile my code with RVIM, so I'm adding the multiplications and divisions, does this code run in every CPU that are flagged as RISC-V? Who says yes? Raise your hand. Who says no? Raise your hand. There is 100% no. Okay, cool. Why?
Because it may include instructions that many other extensions don't get.
Second?
Unless you have that extension, the user will not know what those instructions are. So.
Yeah, okay. So your colleague is saying no, because maybe the other CPU doesn't have the M extensions. And why it doesn't have the M extensions? Okay, but because they are not mandatory. That's what I want you to take home.
Is it possible for the CPU to trap and have the OS go in with a handler and do multiplication in software?
Yeah, that will be yes. But that means, okay, the question is, if I write a compile code for RVIM, so my assembly will actually have the mul. Whenever I wrote the asterisk in my C code, that gets translated to mul. Is this code running on a CPU without the M extension? The answer is no, in general no. So it will trap, it will say illegal instructions, sorry. And then the question is, can I write in software a routine that reads the illegal instructions and understand in C code now that this was a multiplier and then implements the multiplication with add and shift in C? The answer is yes, but it's not standard. It's the way you're doing, which is for sure not efficient, but of course it works. It may work, but the answer is that they don't run exactly in the same way. Okay, so you cannot say your CPU is RVM compliant. It runs multiplication, but it's not RVM compliant. Okay, but yeah, of course you can implement these things in different ways. Got it? So the only mandatory ones is RVI. Given the bit width, we all agree that the code is the same. All the others are up to you. These allow me to design a very small CPU. Why would I design very, very small CPU with only a few bunch of instructions? Because maybe among my clients, or let's say my users of RISC-V, there are people that only need those few instructions to control an accelerator or to control the temperature of my chip or to do whatever basic stuff, right? So this ISA is very nice because it's coping with these guys as well. But at the same time, it's also offering standardized instructions to implement computing stuff. Multiplication, floating and double, precisions, arithmetic, vectors, and so on. We will see them. That's why. Plus, and I said that before, it's modular, customizable. So as your colleague was telling at the beginning of the lecture, he is actually adding custom extensions to his own CPU. It means that RISC-V is, let's say, reserving a portion of the instruction space that is user-defined. So, of course, I know you guys know the answers, but is the code compiled with a custom compiler with custom extensions able to run in every other CPU based on RISC-V? No, of course, right? So, of course, it's not the case for standard ISAs. It's even less the case for custom ISA, because maybe I don't even give you the spec, right? I can implement them and keep them closed source, while these guys are open source. For example, I'm implementing my stuff to be a secret. It's my market advantage, competitive advantage. Okay? As you see, it's modular, flexible. Then another ISA extensions I didn't mention so far is the E. So this time it's the English E, so elephant, RVE. So this is for reduced number of registers extensions. Again, why this is important? Because if you have a very small CPU and you design the pie chart of the area profile of this guy, you may realize, it's not always the case, but oftentimes you will realize that a big chunk of this area is the register file. And if you don't really need your CPU to have more than 16 registers, then what RISC-V is saying is that if you're really targeting super ultra low power applications, very small CPUs, get rid of the latest 16 registers. And now your final area is smaller. Okay? So is a core implementing RVE ISA efficient?
For embedded applications.
For which applications? For embedded application, he said, but for which applications?
Maybe no edge.
Okay, but the real answer is the easiest one, is the universal answer. It depends. It depends, right? It depends what you're running. So if you're running an application that doesn't need this number of registers, it's an efficient extensions. If you need a lot of registers, what happens to this ISA when you compile an application that would require a lot of registers but it doesn't have them? So what does the compiler do?
More loads and stores.
Yeah, towards?
Yeah, moving it back and forth.
Yeah, exactly. So the compiler will emit a lot of load and store to talk with the stack. For example, push and pop in other dialects of other ISAs, because it doesn't have space internally to store data, right? So it will use the memory to do it. So is an application like that, is it efficient or not? No, the answer is not in this case. It's not, it depends. Because if I need, for example, constantly 30 operands, and I compiled in my application with 16 registers only, I will always need to go back and forwards with the stack, which is bad. So it's not efficient. It doesn't depend. It's bad. Because we define the application in this case. We say that the application needs a lot of operands. So in general, it depends. Because it depends on what? On the application. But now we said that the application needs a lot of operands, not efficient. If it doesn't, very efficient. Again, remember, there's no one-fit-all solutions. In this case, going back to the moto and car slides, will be like something that you care about the power, care about the energy. So the goal of whoever proposed these extensions was doing something small, okay, low power. And usually the E extensions is put together with the C, the compressed ones. Is a CPU implementing RVEC bigger or smaller than a CPU implementing RVE without the C? Bigger. Okay, good. It's actually bigger because it has to decode more instructions. So the decoder is bigger because it has both the E and the C. Probably the whole system is smaller because you need less RAM to store your data, to store your instructions, sorry. So maybe at system level it's smaller, but the CPU itself is probably bigger, okay? Multiplications and divisions, do we need them? The answer is? Depends, exactly. So if you're compiling your applications and you have a lot of asterisk and slash, so you're multiplying and dividing, better to have them in hardware. Okay? Is this multiplication done in 1, 2, or 15 cycles?
Not defined by ISA.
Thanks a lot. It's not defined by the ISA. Okay? This was a tricky question. ISA is not implementation. This is the very common mistake I heard a lot of times in interviews, talks, even by senior people sometimes. Like, an instruction is 1 cycle. Absolutely orthogonal topics. You can implement a multiplication in 5,000 cycles or 1 cycle. It doesn't depend on the ISA. Implementation is not specification. So question, if I design an RVIM CPU and my CPU is taking 5 cycles to do a multiplication, and the gentleman there designed his own CPU which is taking 1 cycle doing the multiplication, is the software compiled for his CPU running on my CPU? Yes, because who cares, right? Is it more performant? No. I mean, his CPU is more performant than mine. But the answer of the code is going to be the same, unless it's time-dependent code. Good? Questions?
One clarification, the multiplication and division, they are always together?
Yeah, actually no. Yeah, I simplified, I didn't put this extra condition, but theoretically you can have division and multiplication split. That will be called ZMMule extensions, but yeah, the goal of this lecture and the following is not reading the RISC-V manual, but if you go to the RISC-V manual, which is open source, and it's clearly readable, you will see that there are a lot of sub-extensions to, enable this and that, disable this and that at finer level than the one I present here. Now, we said before, floating point register file is separated by the integer ones. Cool. So that means that I need extra instructions to move data to that register file. Correct? How do I move a floating point number from memory to this register file? Can I use the normal load and store? No, because they target the integer register file, correct? So the load instructions will activate a final state machine in the CPU that emits an address to the memory, gets the answer from the memory, and stores the data into the integer register file. So I need something else. How will you guys implement the floating point load and store? How will you move it there?
You can copy it from the register file of the integers to the register file of the floats.
Okay, so every time you load a number from the memory, you need 2 instructions. One, you load, and then you move. Right?
I want to be like philosophically RISC, yes.
Philosophically RISC, yes, okay. Then, otherwise?
Dedicated instruction.
A dedicated instructions, or?
On what level are we? Like, sure, it can be a dedicated instruction,
Yeah.
but
I'm asking how you guys will do it. There's no right or wrong answer. They're both correct, right? He decided to spend an instructions to do that. He decided to use 2 instructions to do it. RISC-V decided to do like he proposed, having a dedicated load and store instruction that are called fload, fstore. Easy. Okay? Whenever the CPU gets an fload, it knows the destination is the floating point registers. Now again, in the topic of sub-extensions, there is a Z, F, and X sub-extensions of the floating point extensions that says, what did we say before? What is very expensive in CPUs? A register file, right? Do I need to add one? Maybe not. If my code is not really operand heavy, it doesn't require a lot of operands, then I can share the register file together with the integer. So in that case, your application will use the normal load and store instructions to move a floating point number to the register file. So now that the register file contains both integer and floating point operands, how does my CPU know whether it should do an addition with the integer hardware or with the floating point hardware?
The instructions are still different.
The instructions are still different, exactly. So not one will be the additions, the other one will be the F addition, F add, F mul, F div, and so on. So now you can have all these things, right? So you have integer register file with integer only data path, floating point register file with floating point data path. So in that case, you have two different data paths and two different register files. And then, or you can have a single register file and two different data paths, or you can reuse the integer other plus other control and states, final state machines to maybe implement in a, let's say, software way, multi-cycle way, using the integer data path your floating point operations, right? So multi-cycle operand operations. Again, how do I do it? It's implementation independent. No one cares how you do it. Important is to know that if you compile an application with RVIF, has to run in every IRVIF CPUs, but if you implement it with the ZFNX extensions, so you share the register file, then it runs only on, so the F won't run in CPUs implementing the ZFNF, but will be true the other way around, if they support it, okay? Then still under the simplicity design choices RISC-V made is that they have special instructions to deal with approximations and so on, okay, rounding and things like that. Last, vector extensions. Do you know what a vector is? Yeah, I guess most of you know vectors. You probably use them in your C code, like int something, square brackets, blah blah blah, and you write your vectors. Okay. They also define, RISC-V also defines vector extensions. So the operands they refer to is a vector. What a vector is, it's something that usually is continuous in memory. In this case, it's continuous at least in the register file. Vector machines have another register file, wider usually, because it has to contain many elements. Okay? And how many? Implementation dependent. That's specified in VLAN max. Who cares about the name? It's a custom register. It defines in your custom CPU how many elements you have in your register file. Tricky question now. If the two of us design RVV compliant RISC-V ISA, my CPU has 8 elements maximum, and your CPU has 16 elements maximum. Is your code running on mine? Yeah? The answer is yes or no. Raise your hands yes, raise your hands no. Yes? No? And the others? So the answer is yes, right? We say that till now. If you compile one thing with one code, that's the main difference between, let's say, non-vector, like pure CMD machines, where the length is embedded in the instructions, differently than vectors. Because in vectors code, the code itself is reading these registers, and it iterates over the application number of elements divided by the physical register. So for example, if you have 4 elements, but your application requires 10 elements, then you do one iteration with 4, another iteration with 4, and then with 2. If your CPU is implementing 16 elements, it's done in one iteration.
Yeah, just to be blunt, like depends how you write your assembly, because if you increment...
Absolutely, absolutely, yes, absolutely. Of course, if you write it in a wrong way, then it will never work. Yes, but that will be wrong. Yes, but that will be the wrong way. Yeah. Okay? So, vector machines also have floating integers. You can have only integers, you can have both. Similar thing. With respect to the scalar, a single instructions refers to multiple operands, SIMD, single instruction, multiple data. So the VAD is an addition across many elements. And that's it. Okay, let's conclude. We said what edge is. now you know that in this class we are talking about edge devices and not the CPUs used in your servers or in the servers you're using if you don't own a server. You will learn that to be efficient, the answer is always depends, unless I tell you what we have to do specifically. And there's no one fit all solution, it depends on the domain and what I'm gonna do. And we learned about RISC-V, which is an open ISA. Very important, the ISA is not the implementation. Okay? Key takeaway, it's modular and extendable. That's it. So, unless you have questions, we see either at 6 p.m. for those interested in continuing talking about RISC-V or tomorrow, same hour. Bye.